1 minute. That's roughly how long it takes Google's newest quantum chip to run a calculation that would keep the world's fastest supercomputer busy for over a century. Not an estimate, not a simulation, a real, independently verifiable result, published in one of the most rigorously reviewed scientific journals on Earth. And the moment it happened, quantum computing crossed a line. Researchers have been chasing since the field began. Not just doing something a classical computer can't do, but doing it in a way that can actually be checked, confirmed, and trusted by anyone willing to run the numbers themselves. Here's the thing worth clearing up immediately. Nothing about this broke the laws of physics. Quantum computers don't bend reality, they exploit it. They work precisely because particles at the smallest scales behave according to rules classical computers simply can't replicate efficiently. What actually broke wasn't physics. It was a decades-old assumption about what was computationally possible and how long it would take before verified quantum advantage stopped being theoretical and started being real. Tonight, we're breaking down exactly what Google's quantum AI team did, why scientists are treating it differently than every previous quantum computing headline, and what a genuinely current update from just weeks ago suggests about where this is heading next. Let's start with the chip at the center of it all. Willow is Google Quantum AI's most advanced quantum processor. A 1/5 qubit superconducting chip built using circuits cooled to temperatures colder than deep space, close to absolute zero. Superconducting qubits are notoriously fragile. Heat, electrical noise, even faint vibrations can scramble the delicate quantum states they depend on, introducing errors that pile up the moment you try to scale a system to more qubits. For years, that was quantum computing's central problem. Adding more qubits almost always meant adding more errors, not fewer. The exact opposite of how classical computer chips tend to behave as they scale. Willow flipped that expectation. Google demonstrated that its error rates actually decreased as the system scaled, evidence that quantum error correction, long treated as a theoretical requirement rather than a proven capability, genuinely works in practice. That alone represented a major milestone on Google's long-term roadmap toward a fault-tolerant quantum computer, following earlier steps that included the company's first beyond classical computation back in 2019 and an early error correction prototype in 2023. Each milestone built directly on the last, part of a deliberate, publicly tracked roadmap rather than a single unexpected breakthrough arriving out of nowhere. But the moment that actually reshaped the conversation came on October 22nd, 2025, when Google's team published results in the journal Nature describing something they called quantum echoes. Here's what makes this result different from every quantum computing headline that came before it. Back in 2019, Google made global headlines by claiming what it called quantum supremacy, using an earlier chip named Sycamore to complete a calculation in 200 seconds that Google estimated would take a classical supercomputer roughly 10,000 years. It was an important milestone, but it came with a serious limitation. The specific task Sycamore performed, sampling essentially random output from a chaotic quantum circuit, had no real scientific application, and more importantly, its result couldn't be independently verified using classical methods, since the same output bit string would essentially never appear twice in a system that large, making it impossible to check against anything. IBM disputed the claim shortly afterward, arguing a sufficiently optimized classical algorithm could plausibly get closer to matching it than Google suggested. The entire episode highlighted the field's fundamental problem. Proving a quantum computer did something impressive is far harder than actually doing something impressive. Quantum Echoes was built specifically to solve that problem. The algorithm measures something called an out-of-time order correlator, or OTOC, essentially a way of running a chaotic quantum system forward in time, then reversing those exact operations to run it backward again. In a genuinely chaotic system, tiny disturbances normally scramble information almost instantly, the same way a drop of ink dissolves into swirling, untraceable patterns the moment it hits water. Running the process in reverse lets researchers effectively pull that scrambled information back together, producing a clean, measurable signal instead of meaningless noise. Physicist Tom O'Brien, part of Google's quantum AI team, explained the core issue plainly during the announcement. Without a way to independently confirm the data, having an impressive result doesn't actually accomplish much. Quantum Echoes solves that by producing an echo signal robust enough to extract real, verifiable information out of a system that would otherwise simply dissolve into chaotic noise, rather than random one-time use bit strings that could never be checked or reproduced. Running on a 65-qubit subsystem within the larger 105-qubit Willow chip, Quantum Echoes performed its target calculation roughly 13,000 times faster than the best available classical algorithm running on one of the world's most powerful supercomputers. And unlike the 2019 result, this one wasn't an artificial benchmark built specifically to favor quantum hardware. Researchers used the algorithm to analyze genuine molecular structure data collected through nuclear magnetic resonance, or NMR, spectroscopy. The same underlying physics used in medical MRI scanners and pharmaceutical research applied here to actual organic molecules studied at UC Berkeley's Pines Magnetic Resonance Center. The Willow chip's results didn't just run faster. They produced improved models of the molecule's actual structure, genuine scientific output with a real research application behind it, the kind of result that could plausibly feed directly into future drug discovery or materials science work rather than sitting purely as a proof of concept. The scale of the underlying experiment is worth sitting with for a moment. Google's engineering team reported that Willow's hardware, with individual gate fidelities above 99.9% across its full 105 qubit array, roughly 99.97% for single qubit operations, and 99.88% for the more error-prone entangling gates, was capable of running millions of these quantum echoes measurements in mere tens of seconds. Over the full course of the project, that added up to roughly 1 trillion individual measurements, a meaningful fraction of every measurement ever performed on every quantum computer built anywhere in the world combined. Google's own team described the resulting dataset as one of the most complex experiments in the history of quantum computing, a scale of data collection that simply wasn't achievable with earlier generations of hardware, however promising their early results looked on paper. And here's the detail that makes this result genuinely different from anything Google claimed in 2019. It's independently checkable. The output takes the form of quantum expectation values, measurable physical quantities like current, velocity, or magnetization, values that should come out consistent, no matter which properly functioning quantum computer runs the same calculation. In principle, another lab with its own quantum hardware could run the same quantum echoes protocol and confirm Google's numbers directly. As of the announcement, that independent verification hadn't happened yet, but the pathway to prove it, unlike the 2019 claim, genuinely exists, and researchers elsewhere in the field have already begun discussing how they might attempt it. So has this discovery unlocked some kind of unlimited computational power? Not remotely, and Google's own researchers have been careful to say so clearly. Quantum advantage here applies to one specific narrow category of problem: simulating chaotic quantum systems, the exact kind of calculation classical computers handle catastrophically poorly because the computational cost explodes exponentially as the system grows. For the overwhelming majority of everyday computing tasks, browsing the internet, running a spreadsheet, even most scientific simulations, ordinary classical computers remain vastly more practical, more reliable, and dramatically cheaper. What changed isn't that quantum computers can now do everything better. It's that, for the first time, there's a clearly defined, scientifically useful category of problem where a quantum computer demonstrably outperforms every classical alternative, with results anyone can eventually check. Now here's where this story becomes genuinely current, not just historical. It would be easy to treat quantum echoes as a single dramatic headline from late 2025 and leave it there. But the pattern of announcements that followed it tells a more interesting story about where the field is actually heading. On July 17th, 2026, just weeks before this video, Google Quantum AI announced a separate but closely related breakthrough, a system that lets quantum hardware learn from its own errors in real time, using machine learning, without halting an ongoing calculation to recalibrate. Traditionally, quantum processors need to be paused regularly so engineers can manually readjust thousands of hardware settings, since qubits are extraordinarily sensitive to heat, electrical noise, and other environmental disturbances that gradually throw the system out of tune. Pausing constantly for recalibration becomes an even bigger bottleneck as systems scale toward the thousands of qubits future fault-tolerant machines will eventually require, since the number of settings needing constant adjustment grows right alongside the qubit count. This new approach instead lets the hardware continuously adjust itself, based on live error data streaming in during the calculation itself, rather than freezing everything to fix problems after the fact, effectively teaching the machine to correct its own drift on the fly, instead of waiting for a human-scheduled maintenance break. Put together, these two results point in the same direction. Quantum echoes prove that a quantum computer can produce fast, genuinely verifiable, scientifically useful results. The July 2026 self-correction breakthrough addresses one of the biggest remaining obstacles to actually scaling that capability up to larger, more complex, more stable systems capable of running for longer stretches without human intervention. Neither result alone would justify a headline claiming physics itself changed. Together, they represent something closer to the truth. A research program methodically clearing the practical obstacles, standing between an impressive laboratory demonstration and a genuinely useful piece of technology. Google isn't stopping at superconducting qubits, either. In March 2026, the company announced it was expanding its quantum research to include an entirely second hardware approach, neutral atom quantum computing, built by trapping and precisely manipulating individual atoms, rather than relying solely on superconducting circuits. Hartmut Nevin, who leads Google's quantum efforts, described the move as a way to combine the distinct strengths of two different quantum computing approaches rather than betting everything on one, since no single hardware architecture appears likely to dominate every kind of computational problem in the near term. The two modalities, he explained, would allow research and engineering breakthroughs in one to cross-pollinate into the other, giving Google versatile platforms tailored to genuinely different classes of problems, rather than forcing every future application through a single type of hardware. So no, physics didn't break. It held together exactly the way it always has, precisely enough that a chip cooled near absolute zero could run a genuinely verifiable calculation no classical machine on Earth can currently match. What actually broke was the old assumption that verified quantum advantage was still years away. As of October 2025, it wasn't a future milestone anymore. It was a published, peer-reviewed result, sitting in Nature, waiting for the rest of the scientific community to check the math. And that's really the through line connecting all of this. Not one single dramatic announcement, but a steady, deliberate sequence of milestones, error correction that actually scales, an algorithm that produces results anyone can eventually verify, and now hardware that can correct itself without stopping to ask permission. None of it happened overnight, and none of it happened by accident. It happened because a decade of incremental, unglamorous engineering work finally reached the point where the headline could catch up to the reality. If you want to know the moment another lab finally verifies Google's Quantum Echoes result independently, subscribe and turn on notifications, because when that confirmation lands, it'll mark the actual end of quantum computing's decades-long credibility problem once and for all.